Okay, so can we wait for?
Questions.
Sure. Yeah.
So, is there a multi-current algebra? Meaning
Multi-current while module.
no, CT1, T2, etc.
Yeah.
Meaning not just GCT, but GT1, T2.
Mm-hmm.
Would it be interesting to do it? And
It's been so.
or is it included and you're only?
I'm only focusing on this. Yeah. So let me tell you. So in general, you could take G tensor A. So you take a map algebra, A commutative, associative, and so on. Then for that, you can define these while modules. So it is actually an interesting question. So you can define these while modules, global while modules, which you call WA lambda. Okay, and you can also define the local while modules. Okay, and one of one of the things I was going to tell you today is if you take A equal to CT or CTT inverse, okay, then all these are all quotients of your global while module, yeah, and all these quotients have the same dimension. So I'm going to say that, okay.
Sorry, which one? W log.
Oh, let's not do W log. Let's drop the grading, because an arbitrary algebra might not have a grading. So W pi in which, yeah? So this pi will correspond to picking maximal ideals in some sense. Okay. So all these things, you can define these things, and they all have the same dimension if A is a polynomial ring in one variable. Okay. But one doesn't know what all these dimensions are in general. It's not going to be the same dimension, and it sort of depends on the point you choose in the variety.
Even for CT?
No, not for CT.
But more general.
So yeah.
Even for something like CT1, T2.
Exactly. So that and so so what happens is that this WA lambda is a module for the following. So let me just tell you for SLN, this is already a problem. Okay, so WN, SL2 I mean, SL2, okay. So you take A tensor N, okay, and you look at the invariance of it. Okay, SN invariance. Then this is a right module for this algebra. Now if you're working with the polynomial ring in one variable, this is of course again a polynomial ring. But it's never otherwise a polynomial ring. So this variety is very complicated and has lots of singularities and so on. So in some sense, so this WA pi is WA lambda tensor this ring modulo a certain maximal ideal in this ring, which we'll call M pi. Okay? So it depends on what you pick over here, the dimension of this thing. So there is some very interesting geometry underlying this, which you don't see in the one variable case. But one doesn't know what, I mean, so that hasn't been. So there's this paper I wrote, in fact, with Fourier and Kandai, who you know. Right, who's a postdoc here. And in that paper, in the last section, we make some comments about the funny things that happen for these local while modules.
So your paper is Meher Savage.
Yeah. Our paper is before theirs. But Nair and Savage don't do while modules in some sense. They only classify irreducible modules for map algebras. And that is then completely done, both in the twisted and the untwisted case and so on. But these local while modules, I mean, this geometry is not understood. And there are also these things called equivariant map algebras, and that too is not fully understood, except in some. So, I mean
so equivariant map algebras are those defined by the hand.
That's right. Mm-hmm.
But what is not understood? The while modules.
Yeah, essentially.
Have they been defined?
So, The answer is yes and no. So if you, for instance, if they're defined, I think, when are they defined? They're defined if if the group, so what is so there's a group which acts on your variety, right, for the equivariant map case. So if the group acts freely or without fixed point, then one can play these games. It's very similar. But otherwise, it's not known. So that hasn't been studied. And defining these global while modules is a problem. Defining this is such a problem. Oh. Okay.
I also wanted to ask you one more question.
Sure.
I mean, very naively, if you have, say, one of those sim hom g sim, suppose that whatever that.
So you want to take hom G, and then you want to take SK1R1.
Something like that.
SK1G tensor, okay. SKPG, yeah.
Tensor.
V mu. Oh, tensor V lambda, comma V mu.
V lambda and then comma V mu.
Yeah.
Maybe with an R, okay.
Yeah.
So suppose this is non-zero.
Yeah.
Can you say, I mean, I'm just asking very
Sure.
quickly, x of the appropriate, the integer that we started with k1, kr was the partition. I mean, 1k1 plus 2k2 plus rkr was.
It's K1 plus 2K2 plus PKP. Mm-hmm.
Kp was what? So can you say that x star of v lambda r mu, yes?
I don't know. I don't know anything about higher order X in this kind of generality. So, for instance, what Jacob and I studied, so this algebra G tensor CT is huge, right? So what you can do is study truncations of this algebra. So that means you quotient out by ideals like this, graded ideals. Now you're in a finite dimensional algebra situation. So for instance, if you take R equal to 1, it's just a simple algebra, right? And the category is semi-simple. Supposing I take R equal to 2, then this has a name. It's called the Takif algebra. Okay, and what Greenstein and I studied, and then it was also generalized later by Apurva, is modules for that. So now what does that look like? That if you take R equal to 2, then this is just 2 copies of G, and this is like an ideal. So this looks like GT. Right? So this is an ideal. Then what happens over here is then your projective, so you can play this whole game that I described, and now your projective module in this context is just S of G tensor V lambda, because this is a commutative thing. So its enveloping algebra is just S of G. And so then you can play this game. So there you can compute the X ties. Because you have, so for the symmetric algebra, you have the Koszul complex. And so you can use that to compute X.
And it's of infinite.
No, it's a finite global dimension.
Finite global dimension. And equal to?
No, it's not always a finite. You have to cut your category, and then it's a finite global dimension. It's not otherwise. And then you can describe what the global, so you can say what all the global dimensions are. But it's not entirely trivial.
Another question, you know the blocks of G?
Yeah, of this category. So for no, so if you're doing G tensor CT or CTT inverse, or the blocks of G, I don't know what the blocks of G are, but I can tell you what the blocks of finite dimensional representations are. So blocks of the category of finite dimensional representations. That is, those are given by maps, sigma, finitely supported functions from C star. So finitely supported functions from C star to P by Q, weight lattice by root lattice. So the blocks are huge. And in the case of G tensor A, this result has been generalized, the blocks of this, by a guy called Codera, R. Codera. Okay. And there is something funky that shows up, which you don't see over here, that you have to somehow, the tangent space matters. So, I mean, these are points, right? So these are maximal ideals. So over there, you would replace it by maximal ideals for your underlying variety. And then some of the tangent space matters, and m by m squared matters in describing these blocks. But I don't know how to. And then I think, so this was done by Codera, and then the equivariant case was done by Nair and Savage. But the methods used, so both he and I mean, so this I did with Mura, and so both papers use Weil modules, which is not available for equivariant map algebra, so they use some other kinds of techniques to do this, to compute cohomologies. So the blocks, unfortunately, are very big. So they're unlike in the category, oh, they don't give you enough information. So if you're doing E8, for instance, this is just, everything is in one block, because that's a trivial group. So it's not.
And that's because you're P by Q. Right?
P equal to Q, yeah. Mm-hmm.
Okay, but blocks of G themselves you don't.
No, no, I would think that it's something similar, but I don't.
The whole thing, I mean, blocks are big. Is that what? Similar?
Yeah, I would say that the blocks are very big. Yeah. Yeah.
Thank you. Sorry if I.
No, that's all right. So are there more questions before I continue? Okay. So I'm going to say more about this in particular, which will explain some of these things today. Next time I'm going to bring an overcoat when I lecture him. Okay. So now I want to talk in more detail about these local and global Weil modules. So we had so let me write. So this is our global Weil module. W lambda R, whose definition I'm not going to write again yet. And then we have our local Weil module, which we denoted as W log lambda R. Okay? And as I've said many times, these local Weil modules are finite dimensional, and today I want to sketch a proof. So dimension W log lambda R is finite. Okay. So this is a theorem, if you like. And in fact, one can say exactly what it is. So the dimension of W log lambda R is equal to product dimension W log omega I R, all raised to SI, I equal to 1 to n, with summation Ri Si omega I equal to lambda. So for instance, in particular, for SL2, what does it tell us? It tells us that W log NR is equal to W log 1R raised to n. Yeah? And what can W log 1R be? Well, we know it has to start with this as the highest weight representation, which will occur with multiplicity 1, right? V1. And what can I add, if anything? Only dominant integral weights, which are less than or equal to 1, right? And there is no such dominant integral weight, because 0 is not less than or equal to 1 in this partial order. Yeah. Plus weights, n such that 1 minus n belongs to q plus, right? There are no such weights. So this means that W log 1r has dimension 2. And so, in general, the Weil module, local Weil module, has dimension 2 to the n. Okay, so it's an absolutely enormous module.
But it could have V1 in the next grade, right?
No, W log has the top weight space one dimensional. I mean, it has the one, what are the relations? It's n plus tensor CT. I can't get out of writing it. Yeah. So W lambda r is 0, and HT power r W lambda r is HT power s W lambda r is 0 if s is greater than 0. I mean the local module. So the lambda weight space is one dimensional, independent of the grade. It's not just the lambda r weight space. In this module, it can have lambda in the next grade, but not in the local module. Okay. So how does one guess such a theorem? Well, that's why I spent time telling you about representations of quantum affine algebras, because that was the only reason to guess such a theorem. Because this is supposed to be the classical limit of the quantum affine algebras representation, and that you knew was a standard module, and you proved theorems that it was a tensor product of fundamental representations, and the fundamental representations specialized to these modules, Weil modules, and therefore this was the conjecture. And once this conjecture is proved, then in fact it says that that module specializes to this. So this was the motivation for the conjecture. So this was so this part was originally a conjecture due to myself and Presley, and then it was proved by. This is a fairly difficult theorem, which was proved over 10 years, but now this is actually a theorem. Okay. Originally it was just a conjecture. So I'm certainly not going to try and prove this theorem, but let me at least tell you how to show that W log is finite dimensional. So proof for SL2 that W log n is finite dimensional. Okay. Okay, so the top weight space, as I've said, so if you look at W log n,
So the R is just there for the...
for decoration, so I'm going to drop it if you don't mind. So, and in fact, the proof will be the same. So W log n, the n-dimensional weight space is C. We've agreed on that. Right? The top weight space is one-dimensional. Okay, so what is W log n? N minus 2 going to be spanned by? So to get to this weight space, I can't apply anything from n plus t. Right, so I have to apply something from n minus t. And in the case of SL2, what is n minus t is just y tensor t power n, right? And if I only want to do this, then this is spanned by elements of the form. So y, my SL2, so my standard basis is xyh. So it's spanned by y tensor t power k, wn, where k is in z plus. Right? That's all it can be by Poincare-Birkhoff weight. Now, these are obviously infinitely many vectors of different grades because the k varies, right? So if I want to prove that my weights, I better prove that this weight space is finite dimensional, otherwise my module is not going to be finite dimensional. So I have to show that these elements are 0 for all but finitely many k, right? So we must show that y tensor t power k, wn, is 0 for all but finitely many k. And I mean, you can't have spans because they're linearly independent if they're non-zero. Okay, so how are we going to prove something like this? About the only tool you have then, right, if you want to show, I mean, this is an abstract module given through generators and relations. So the only tool you have is this wonderful formula of Garland. So let's review what Garland's formula is. So Garland actually did something quite miraculous, as I said. He took y power s, x tensor t power r. This is divided powers, so let me just use that notation. And he rewrote it in Poincare-Berkowitz basis order. Okay? So he rewrote this element. In Poincare-Berkowitz order, which for us was as an element of un minus t. So UHT and UN plus T. Okay? Now, how did we get our condition on the p's, for instance? You know, we said that all the p's had to act by scalars when we did that terrible calculation. How did we get that condition? We took r equal to s, right? Now, what do I want? I want 1y left over. So I don't want it to be grade 0. So that means what do I want to do? I want to take r to be s minus 1 and inspect what Garland's formula tells me. And what Garland's formula tells me, so you have to unravel it, and it tells me that x tensor, so we have y to the s equal to 0 if s is bigger than or equal to n plus 1. And now using Garland, I get this x tensor t power s, y power s minus 1, y power s. On the one hand is equal to 0, and on the other hand is equal to summation k equal to 0 to s minus 1 yk p I should have a wn there, yk p s minus 1 minus k wn equal to 0. This is Garland's formula. You just have to take it. This is the part which has a 1y left over. Okay? What will the other terms look like? They might have 2 y's on this side. But because of weight reasons, there would have to be an x on the other side. And the x would kill the wn. So it's the exact same argument that we understood for p's, only in this case. Okay. What does this equation tell us? What is p0? P0 by definition is 1, right? And P1, what was P1? P1 was something like minus H1. P2 was something like minus H1 squared over 2 minus H2 over 2. Or maybe it's plus, yeah? So what do all these PI's do to my local while module? They all? Oh, y tensor t power, okay, sorry. Okay. So what can I say? So now all these things on Wn are 0. Do you agree with that? Because H1 is, so let me use this notation that HK is H tensor. I understand it's confusing outside this rank, but that's what I mean. So this is H tensor T1, H tensor T, let me just write it. And then this is minus H tensor T all squared by 2 plus H tensor T squared by 2, Wn equal to 0, right? Because all the H's acted trivially. So what does this equation now tell me? What is the only term which survives? The only term which survives is when this is P0, which is 1, right? So this means that I get that y tensor t power s minus 1 Wn is equal to 0 for all s greater than or equal to n plus 1. Are we agreed with this? Okay. So that means I've now proved that my W log n minus 2 is spanned by finitely many elements, and in fact, I only need to go from 0 to n minus 1. Because if I take s equal to n plus 1 over here, I get y tends to t power n wn is 0. Okay? All right, so now I claim it's immediate that all the other ways are finite dimensional. Why is that? And hence, 2 more steps. So this I claim implies that W log W log n minus 2r is finite dimensional, 2p is finite dimensional for all p. Why is that true?
All of us are product of
Yeah.
product of this y power y tensor equals.
And there's one more point that you must make. So the next, I mean, if you're doing n minus 4, it will look like this, right? Right? On Wn. Now what you're telling me is that this is bounded. Correct? Why is this bounded? You haven't told me that. What can you say about these two elements? Their commutator is 0, right? So you first bound this, then you go in and you bound that. Okay? And so now you've got that 0 less than or equal to r. I'm trying not to use r, but failing. But anyway. So over here you only need to. So what is the dimension, therefore, of. So what do you think is the maximal dimension of this? So to get a term over here, I have to take a product of py's, right? So, and then if I take py's for each of those things, I have n minus 1 choices. No, I have n choices, so this dimension is less than or equal to n to the p. So over here, when I went down only 1, I had n. If I go down 2, what you just said was that you get n squared and so on. Okay, so you have n to the p. So have I proved now that it's finite dimensional? I've proved that every weight space is finite dimensional. So to prove that it's actually finite dimensional, what do I need to prove? That there are only finitely many weight spaces. So why is that true? So now, so to complete the proof, we must show there are only finitely many weight spaces.
That's true even for W factor W low.
Only finitely many weight spaces? Yeah. Why is that true? So, okay, so you're transferring the question. Why are there only finitely many weight spaces?
But by definition for W global, because you create all the high weight spaces.
There can be lots of weights below lambda. I mean,
But integrable, right?
it's because it's integrable, exactly. So because it's finite dimensional, if you have lambda a weight, if n is a weight, then or m is a weight, then minus m has also got to be a weight, and the weight can't go beyond n. Is that clear? Yeah. So because so you have to show that. So it's an exercise that you do, which is so it's a simple SL2 exercise. Since W log n is finite dimensional, prove that W log n p is 0 if, or is non-zero only if minus n less than or equal to p less than or equal to n. This is a simple SL2 exercise, and then you're done. Okay? So I've proved that my while modulus, at least for SL2, I've given you a proof. The proof adapts. You have to be very much more careful in the general case, but it adapts. But as you can see, so what is the bound that I get from this fairly crude argument? The bound that I get for W log n for the dimension is that it's less than or equal to 1 plus n squared plus y n to the n, right? Because the top weight space is one dimensional, next weight space was bounded by n, next weight space by n squared. So this is the bound. And what was the actual bound? The actual theorem was that the dimension of W log n is 2 to the n. Right? So I have to show, so to prove this theorem, what do I have to prove? I have to prove two things. I have to prove that the dimension is at most this. I also have to prove that the dimension is at least this. Right? So let's see how to prove that the dimension is at least this. So if you were following the stuff on quantum affine algebras, then it should be clear. But let's do a small example to see. And there's a nice construction of Fagan and Lochtel, so I'll just briefly say that. But let's take, so for n equal to 1, I just told you why, before we started, I told you why this was V1, okay? So for n equal to 2, I've given you a construction actually, so this is W log 2. I want to prove that the dimension of W log 2 is greater than or equal to 4. Okay? In this case, to prove that is actually, there's not much that, okay. So how will I prove this? Well, you remember I constructed for you a module which I call G direct sum C. Right? You take the killing form and projection and so on. So for SL2, what is the dimension of G? It's 3. This is 3 plus 1 is 4. Yeah? And I claim this module G direct sum C is a quotient of W log 2, which would prove that. Okay? So this is an exercise. I'm going to leave this claim as an exercise. But even in this case, to prove that this W log 2 has dimension exactly 4, you have to do a bit of work. So let's write this down. So W log 4, what is it spanned 2? What is it spanned by? By our discussion today, it's spanned by the element Wn, right? Then after that, I have to apply Ywn, Y tensor Twn. Yes, exactly. Yeah. That is a maximal finite dimensional quotient. In our graded piece, yeah. Mm-hmm. So that's. Can I finish this and come back to that? Yeah. So so I'm trying to convince you that W log 2. So this tells you that this dimension is at least 4. And I'm now trying to convince you that this dimension can't be more than 4. Okay, so this is exactly 4. Okay, so it's spanned by W2, YW2, Y tensor TW2. Yeah, and we're agreed that you don't need any more because Y tensor T power 2W2 onwards, T squared W2 onwards was 0. That's what I checked. Okay, and then at the next level, what do we have? We have Y squared. We have Y tensor T. And we have Y tensor T all squared. Okay, this is W2, W2, and W2. Okay? Because you can only take monomials in what appeared before, because it got bounded, right? So I have more elements than I want, and I want to get rid of some of these elements, otherwise I'm in trouble. Okay? Okay, now you start with W2, yeah? This is but for SL2 reasons, this can't be 0. Right? Because this is dominant integral weight. So the first time any power of y kills it is if you go to y cubed. Okay, so this certainly can't be 0, so I can't do anything with that. Now supposing this was 0, right? Then these two would be 0 as well. Correct? Then my dimension is too small. Then my dimension is 1, 2, 3, and I know it must be at least 4. Okay? So this is definitely non-zero, because for dimension reasons. Okay, so that means if I want my dimension to be 4, I have to get rid of these two terms somehow. Otherwise, I'm in trouble. Yeah? So how will I get rid of these terms? So let's look at y tensor t of W2. When you apply x to it, what happens? X will move over W2 and kill it. When it moves over, it produces a commutator, which looks like h tensor t. And h tensor t, by definition, killed W2. Yeah? What is the weight of this element? This element has weight 0, right? 2, 0. And it's killed by x. That means y better kill it. Trivial module, right? Since y tensor t W2 has weight 0, SL2 theory we get that y tensor t W2 is equal to 0. So this is 0. Okay? And now, to check if you've understood this, I'll leave you to prove as an exercise that this is 0. Okay? It's just playing with commutation relations. Okay? So unless you can do simple examples and calculate, you don't learn enough about the theory. So this tells me that the dimension is 4. Okay, so before we continue, so what was this? So the question was, why does W lambda, the global wild module, have this local wild module as, yeah. So let's suppose W, so I'm trying to prove W log lambda proposition. W log lambda is the maximal finite dimensional quotient. I want to put in lambda r now. I want to keep that, otherwise it's not a meaningful statement, of W lambda r. And what do we mean by maximal? Well, what I mean by maximal is any other finite dimensional quotient of W lambda r is actually a quotient of W log lambda r. Okay? And maximal finite dimensional quotient in our category. So the proof is very simple. I should really call this a lemma. Okay. Is it so simple? No, it's not true. No, this statement's not true. Because you can have, no, this statement is not true. It's only any other highest weight is the maximal highest dimensional quotient. If you demand that this h's act by scalars, it's okay. Yeah, but not otherwise. So I won't. Yeah. Mm-hmm. How can I give you an example? Oh, yeah. So I can give you an example. So let's look at SL2 and let's look at W1R. Okay? Then in an exercise, one can prove that this is an easy exercise, really. You can prove that it's just V1 tensor CT with our favorite action that I defined earlier. So the action over here is xt power s on V tensor F equal to xv tensor T power SF. So this is isomorphic to that. Okay? So you have an explicit realization of the global Y module in this case. Okay? And if you just take V1 tensor Ct by T squared, this is manifestly a finite dimensional quotient, but it's not loc. W loc. W loc, on the other hand, yeah. So you have to have this further distribution. Okay. So if you inspect this proof, what it should convince you of is this is obviously not the way to prove a theorem, because the calculations here are just too detailed and so on. So you need some nice way to prove that the dimension is big enough, which is not constructive in this fan, and then you need to somehow see how to get rid of these things. Okay? So there is a classical construction which doesn't use quantum algebras to construct these modules. So this is a construction which was given by Fagin and Loktev. Okay. And they called it the fusion product. Okay. So what you do is you start with let's say k representations of G. Okay? So we call it V lambda 1 tensor with V lambda k. Okay? And then you can consider, you take different evaluations and you consider this module. V. You take this tensor product. And you take the highest weight vector, and that, so V is equal to, let's call it V0, is equal to V lambda 1 tensor V lambda. Okay? Now what I'm going to do, of course we know that this is an irreducible GT module. Okay? But yeah. Yeah. So of course I know this is an irreducible GT module, but this is not graded. This does not live in my category, right? Because how does H tensor T power R act on just a single evaluation? On V lambda, it acts as A to the R H V lambda, right? This is not a graded relation. So this is not a graded module. So it's an irreducible GT module, but does not live in my graded category. Question?
So the AIs are distinct elements of C?
Yeah, AIs continue to be distinct elements of C. Yeah. Mm-hmm. So what that construction does is to somehow deform this module in a way to make it live in my category G. It will destroy the irreducibility, it preserves the G module structure, and it will become an indecomposable module which lives in my category. And when I do that, then, so let me write, so Fagin and Loktev describe a procedure to deform this module to be in G. Okay? I'll tell you this procedure in a minute, but let's see what the consequence of the, and in which, to be in G, and it will have the, okay, and they denote this by, and denote it by v lambda 1, so star. So let's write it as ev. Let's ev a1 v lambda 1 star tensor. So that's why it's called fusion. You're replacing tensor by this star. Okay. Yeah.
So we could have just pretended the whole thing lived in one graded piece,
Which whole thing?
this tensor product.
What does that mean by pretend that it's not a graded module? The action won't be graded.
The action would be graded.
No.
Okay.
Xt power out
Yes.
has to live in the rth graded piece, right? So you can't do that. You have to be cleverer. Okay, so they describe a procedure to deform this module in this way. Now, when you deform this module in this way, whatever you get depends on these parameters, right? And their conjecture is that, in fact, it's independent of the choice of parameters, and that's not known. So let me tell you this procedure to deform it. And then how it ties with local Weyl modules. So the procedure to deform it is the following. So you look at, so you consider the following filtration. Increasing filtration. So you start with 0 contained in u of g of that vector v0, contained in u of g, u of gt, s, direct sum s equal to 0 to 1, v0, and you can imagine what the next one will be, s equal to 0 to 2. I can't write direct sums, so I have to do that. Summation s equal to 0 to 2 UGTS V0. Okay, so this is an increasing filtration. You first apply the grade 0 piece to UG, then you apply all grade 0 and the grade 1 piece to V0, and grade 0, grade 1, grade 2 to V0, and you continue. So you get an increasing filtration. And then you form the associated graded space. Okay? So the associated graded space, so form the associated graded space. Okay. So let's give this F0, F1, F2. Okay. So that is summation Fi of Fk by Fk minus 1, k equal to 0 to infinity. Okay. And then, so you define a GT module structure on this in the obvious way. So yeah, there's only one way to do that. So you, I want to keep this thing so that I don't have to write it again. Oh, actually, yeah. Yeah, so you take, so supposing I take xt power s, and I take some element m, where m lives in fk by fk by fk minus 1. I just pick a pre-image, so m bar, m in fk, coset representative. So this is xt power s acting on m, and I go bar. the obvious thing. You have to check that it's well defined, that's all. Okay? Then this module, this what you get, is what they denote by this. Okay? And that's it. So by construction, this is a graded module. Yeah? So, so the module obtained in this way is graded, and they denoted it by fusion. Okay? So actually graded and denoted as fusion here. Okay? So this module that I'm getting depends on my choice of parameters a priori, right? And the conjecture that they have is it's independent of the choice of parameters. Conjecture, it's independent of choice. This construction, so the result, the module, the graded module so obtained, this lives in G. The graded module is independent of the choice of parameters. Yeah, A1 up to AK. Okay. And so this conjecture is known for SL2. Maybe they even proved it for SL2. But in other cases, it's only known for certain special representations. Not known in full generality otherwise. Other facts about this fusion that one needs to know is the following. It is so before, yeah. So it's actually the conjecture is also known for fundamental representations. So, yeah, and in fact that's okay. So the conjecture is also known for fundamental representations when all the lambda i's are fundamental. No, I don't want to make such commitments. But for SLN, this is correct. When all the lambda i's are fundamental, and G is SLN plus 1. So, I mean, it is known in some other cases, but I don't want to go into that at the moment, okay? So other facts about this fusion. Say that again?
It doesn't notice the number of factors.
What do you mean by it doesn't notice the number?
K representations.
Yeah.
This filtration doesn't somehow recognize that.
No. So other facts about the fusion which are useful, if you take the fusion of k things.
So meaning if A1 through AK or A1 prime through AK prime is the same, or even K does not matter?
No, k will matter. I will explain why.
Okay.
So it's A1, I mean, so the fusion of k things cannot be isomorphic to the fusion of L things.
Okay, so that when you say independent of the choice of parameters, that K is fixed.
K is fixed. K is fixed and lambda 1 up to, actually, sorry. K is fixed and lambda 1 up to lambda k are fixed.
Okay.
Right. Yeah. For a fixed choice of lambda 1 up to lambda k, yeah, that's all. The fusion, so if you look at this fusion, so let me just write. So now let me just suppress this. So if I look at this, and when I write it like this, it means I don't care what the parameters are. As G modules, these are just isomorphic to V lambda 1 tensor V lambda k. So all this funny stuff that you did did not destroy your structure, your G module structure. It remained isomorphic. Okay? And in fact, if one looks at this calculation a bit more, what one can prove is that V lambda 1 star V lambda k is a quotient of W log lambda 1 plus lambda k. So if you look at the tensor product of the highest weight vectors over here, okay, then you can prove that that has all the relations that W log satisfies. Okay, that requires some work, but it can be done. Corollary to this construction then. Let me tell you the corollary for SL2. Right? What is it telling me? It's saying, what is this, how can I use this result? It's telling me that W log n, right, has this quotient V1 star, V1 star, V1 n times, which is what I want to the n. Right? So it has this quotient V1 star, V1 star, V1 n times. So that means that dimension of W log n at least is greater than or equal to 2 to the n. Okay? So this is and this proof works. You can give this kind of idea in general using their results. So what it does for you is establishes a lower bound for the dimension without having to go to the quantum case. So you can understand the whole theory post facto using classical constructions. Okay, so where was I? Yeah.
W log of Wi, they know.
W log of omega I is unknown, yeah. Yeah, so, yeah, so W log omega I is known for algebras of type ABCD, E6, no, F4, G2. And for E6, E7, and E8, there are problem nodes, which are the same problems which occur in standard monomial theory. But if you stay away, so it's known for most nodes of E7. Most nodes of E6, E7, E8. Problematic in the same way that they're problematic in standard monomial theory, you know, the trivalent nodes and things close to the trivalent nodes. In the quantum case, it is known, but that doesn't mean it's known in the classical case. You can't deduce the classical result from the quantum result. And there are certainly there are conjectures for what it is, but in general. So I can tell you, so for A, W log omega I is just isomorphic to V omega I. Why is that true? Because there's no, the omega i's are minuscule, and so there's no dominant integral weight less than or equal to omega I. Yeah? So for Bn, for instance, and also for Dn, let's stay away from the spin nodes, they're special. W log omega I is equal to V omega I plus V omega I minus 2 plus so on, down to, well, you go down to V omega 1 if it's odd, and otherwise you go down to C, going down by a difference of 2. So you have to think of omega 0 as C. And in fact, the way to construct this module is just, in this particular module, can actually be constructed exactly by generalization of the argument, you know, where you take phi going from here to here. I mean, V theta. So you have a map from V theta tensor V omega I to V omega I minus 2. You use that to go down that, and then from here to here, and so on. Okay. So this is actually written in a paper with Murab. which appeared in Communications in Math Physics, and whose name I don't remember. But it appeared sometime in 2000 something, 4 or 5. Anyway, we have only one joint paper in Communications in Math Physics, so it's okay.
This may be a vague question. Is there a path for?
Yeah, this is so. For this, but path models are quantum, right? Usually. So that.
But then you can reduce. For example, or is there a tableau theory?
Yeah, so there are these papers of various Japanese. So I think, so there's crystal-based theory. So once there's crystal-based theory, there's all these other models as well. So there are these two guys called Naito and Sadaki, who write lots of papers on path models for Kirillov-Reshetikhin modules, and these are special examples. These are precisely, if you like, the specialization of the Kirillov-Reshetikhin module associated to omega I. And then there's also these tableau things. I think there are these people called Nakanishi. But those are all at the quantum level in some sense. So you need the Qs in there. Okay. So as I said, one way of proving this, this result that Loktev and I proved, so this dimension of W lambda being equal to this product W omega I raised to Ri equal to dimension actually implies, together with the statements that I made, it actually implies that W lambda is isomorphic to the fusion of these W omega I's. Yeah. Now, of course, when I write it like this, I'm being imprecise because there are parameters which show up. Okay. I remember I said I have a quotient map like this, and now the dimensions are the same, so they're isomorphic. And I'm being imprecise because there are parameters. But I'm allowed to be imprecise because this module is defined independently of any parameter. Yep. This has just relations, ht power r equal to 0. Yeah.
Those are W's?
Yeah, those are W's. So these are defined independent of parameters, therefore this isomorphism doesn't matter. And yes, those are W's, and although I defined it here only for the V's, you can actually define it more generally. Okay? I defined it for the V's because it was enough for SL2, but you can define this in a more general, the fusion products are defined more generally by the same people. Okay? Okay. Right. So, do we have stamina to continue? So are there any more questions about this? Because I'm going to switch gears to global while modules.
So are the V omega 1 at the tail end of that decomposition, that's a 1 or a 0 depending on parity?
That's what I wrote. Omega 1, and I have a C over there hanging around like a spare part.
C was an eraser.
No.
Okay.
It goes down either there or there, depending on parity. You know? And this is the I is not spin. Okay, yeah, sorry, what's your question? No, that's it. I just wanted to say that here I'm assuming that I'm away from the spin nodes. The spin nodes are just, if omega I is a spin node, so if it's omega n or omega n minus 1, then those are minuscule. Those are minuscule again, right here. Yeah, I think they're minuscule actually.
So this conjecture is true for those cases?
Yeah.
CDF4.
Sorry, the conjecture is true for these cases?
Because we know that what is W omega I.
Yeah. But there is no conjecture in this case, right? Because this is not the fusion of anything. Omega, I mean, you can't, this is not going to be, omega I can't be written as a sum of two different fundamental weights, right? Two different weights, I mean, so it's not the fusion. So there is nothing.
That can be omega log omega I as compared to V of omega I. Case E.
Yeah,
Can be used to prove that.
yeah, that can be.
So again, the B and D again, it only lives in the degree R piece or degree 0 pieces.
No, so if I start with degree 0 here, then this lives in the 0 bit, this lives in the 1 bit, and so on. Next one lives in the 2 bit.
This is just as G modules.
This is just as G modules, yeah. The GT module structures are defined by suitable maps going from here to here. All these maps are sort of one-dimensional. There's a unique choice, and you can make that happen. Up to scalars.
Could you repeat this last bit against the W lambda?
So supposing I prove this, okay? Grant me the fact that I've told you how to define fusions of local Weil modules as well. Everywhere there's loc, okay? So if you grant me that, and you grant me the fact that I have a surjective map from here to this, right, which I said that for evaluations, but it's true in this context, then these two obviously now have the same dimension, therefore they're isomorphic, right? How are these modules defined? There is no A1, A2, AK in this definition, right? There is in this definition. So if I change, but this is still isomorphic to that. So if I take another set of parameters, B1, B2, Bk, it's still isomorphic to W lambda. Therefore, these two are isomorphic, and therefore it's independent of the parameters, and so Fagin and Lochte follows.
So this fusion product requires parameters, even if it's not an evaluation module.
Yeah,
Okay.
yeah. It's a shifting of grade.
Okay.
So you're saying, sorry, the conjecture is therefore proved?
The conjecture is proved for these kinds of modules. Fagin and Lochte have a conjecture for arbitrary lambda 1 up to lambda k. But here I'm only fusing omega i's. So they're only proved for fundamental representation. There are special cases known in other cases. So, I mean, there are all kinds of interesting problems here. So, you could take, so I got asked this question, for instance, this year in Germany. Supposing I take W log lambda and I tensor it up with W log mu. What can I say about this module? It's a finite dimensional module. In a good world, I'd say that I have a nice filtration, but that's not true. So the question is, what can I say about this module? Is there anything intelligent to be said? So what is the first thing you would want to do? You would take W lambda tensor W mu, right? And you would want to look at the UGT module through W lambda tensor W mu. What is clear is that it has a quotient. It is a quotient of W log lambda plus mu. I mean, we'll have to worry about grades, but let's assume we're worried about that. This is clear. Okay? But what quotient is it? What am I picking up somehow? So, you could ask what kind of filtration, interesting filtrations does this have? Can you tell it? The Jordan-Holder series might not be quite so interesting because you know the G module structure of both these things. So there are sort of fairly straightforward questions which you can ask, to which one doesn't know answers. And
You said the Jordan-Holder series is not interesting.
well, I mean, you know the G character of this module, right? It's just the tensor product. And you know the G character of this module.
Okay.
So in principle, yeah.
That makes sense.
I mean, so if you think that this is all coming from characteristic P and algebraic groups and so on, then what you would want to say is that this tensor product has some filtration by local Weil modules. Right? It has a filtration such that the successive quotients are local Weil modules. But that's too easy, because this module that you have over here, it will generally be a proper quotient of this rather than isomorphic. So it doesn't even start. So, and it doesn't start for simple reasons. So then you have to keep tweaking it so that it makes you do what it has a chance of giving you what you want, but I don't know. So anyway, so as I said, I mean, Katerina Stroppel asked me what one could say about this, and I realized that there wasn't very much I knew about it. But these are all, I mean, in some ways, these are interesting questions to ask because they're connected up with other stuff. So it's connected up with theories. You know, there's this thing called Schur positivity. So Schur positivity says, supposing I take two Schur functions, right? So I look at the difference. I take lambda mu and lambda prime mu prime, take their character, look at the Schur functions. When is the difference a non-negative linear combination of Schur polynomials? Schur polynomials form a basis for the ring of symmetric functions. That's called Schur positive. So if you're given two pairs of partitions, you say that the question you ask is when do you have Schur positivity? And that seems to be related to these local Weil modules. So these are interesting questions to answer for different combinatorial reasons as well. But doesn't mean I can answer.
We're asking what does this function?
A non-negative integer linear combination of Schur functions. Schur functions are a basis for the ring of symmetric functions. Okay. Therefore, if you look at the difference of two Schur functions, you can write them as a scalar linear combination. And you're asking when is it? And in fact, you can show quite easily that it will be, using representation theory, I think you can show quite easily that it will be integers. The question is, when are they non-negative integers? That's called Schur positivity, and there's lots of work in combinatorics in that area. And so somehow all these kinds of questions seem to be related to this as well. Okay. All right. I propose we stop now. Yeah, is that all right? And so then tomorrow I'll have less to prepare for tomorrow morning.